Hi, I'm Mark Fletcher, Avaya's Product Line Manager for Public Safety Solutions, and this is the Future of Emergency Communications, Next Generation 911. On today's webinar, we'll be looking at who Avaya is, our changing 911 industry landscape, reasons of why we need to move to Next Generation 911, Next Gen 911 and Avaya's role. We'll introduce you to Persistent Contextual Collaborative Conferencing, or PC3. We'll look at some resilient ESInet backbone networks, and we'll conclude with where you can find more information. Who is Avaya? We help companies and governments leverage communications and collaboration more effectively to deliver better results. We provide unified communications, contact centers, data solutions, and consulting services directly and in conjunction with our channel partners to leading businesses, governments, and organizations worldwide. In the public safety space, we enable call handling in about 60% of the U.S. PSAPs, and that covers about 70% of the call-taking positions. The existing 911 network is 44 years old this year. The technology curve for personal communications is constantly accelerating with the new every 2 rule. Unfortunately, on the public safety side, they're lucky if they get new every 22. That creates a large gap in communications technologies between the two sides. You see, today's technology is limited to voice over legacy TDM analog trunks, while in Next Generation 911, the target is to add SMS, video, data, email, and instant messaging. When the existing network was designed in 1968, user locations were relatively static, and routing could be done through a simple database correlation using the telephone number as the key. Next Generation 911 clients, however, will be more location aware, requiring us to geospatially and dynamically route callers. The network topology of today's 911 network is extremely localized, and very little to no connectivity outside the defined geographic area exists. Next Generation 911 aims to eliminate or at least significantly reduce any geographic boundaries and provide a ubiquitous emergency services network that spans cities, counties, states, and even countries. Where today's network is built on proprietary protocols and a closed network environment, Next Generation 911 is built on open NENA i3 standards and is fully interoperable with peer networks. Now, in order to deliver this environment, a new IP-based network is required for Next Generation 911, as you simply cannot deliver these target capabilities over today's analog-based infrastructure that is capable of conveying audio and multi-frequency tones. As we said, the 911 network today assumes that a telephone number equals a location. Now, the architecture is simple, and when moves, adds, and change work was predictable and locations were relatively static, it served its purpose for many years. However, the reality today is that users are becoming more nomadic. A telephone number is the last thing that correlates to a location. We're dealing with more complex environments in both the public and private network space, and moves, adds, and changes are unpredictable and quite often undetectable. This creates a huge disjoint between user requirements and network capabilities. Back in 1968, in Haleyville, Alabama, 911 was implemented for a single reason: single number access for all users for any emergency service. It was designed as a convenience to the 911 caller, so they wouldn't have to remember specific 7-digit numbers for different services. In its initial state, no automatic number identification or automatic location information was delivered to the 911 call taker. Basically, the phone rang and they answered it. That network remained functionally static until about the early 80s, when functionality was added to the network that enabled the delivery of ANI, or automatic number identification, to the 911 call taker that then allowed the call taker to call back the caller in the event that the line was disconnected prematurely. At this point, however, location information was still a mystery. In the mid-90s, the ALI database was introduced that associated specific telephone numbers to a specific street address based on SOI records. The Master Street Address Guide correlated those street addresses with emergency service numbers, which designated PSAP routing. Call takers could then take the ANI received on an inbound call and then perform a database dip or query into the ALI database, where the associated location information could then be displayed on their computer screen. That gave us the E911 system that we know today. Unfortunately, today's networks are not agile enough to deliver multimodal next-generation 911 services. They lack the ability of delivering multimedia content. They depend on inferior protocols and technology and have very little capability for interoperability as they were designed as closed networks. They rely on copper-based TDM circuits and legacy switching gear, so the total cost of ownership is skyrocketing as this infrastructure is quickly depreciating as the public moves forward with IP-based communications and networks. At some point in the near future, maintaining the existing legacy TDM 911 network will no longer be financially feasible. In 2002, Voice over IP was in its infancy. However, companies like Vonage were emerging and provided internet telephony to residences. The NG9-1-1 architecture was designed to prove that IP carriers could connect with the legacy 911 infrastructure to provide basic 911 service to their customers. In most cases, ANI and ALI information wasn't provided, and internet carriers were often establishing connectivity to 10-digit numbers and administrative lines within public safety. In 2005, Voice over IP providers started taking advantage of the Selective Router E2 interface that provided the ability to utilize a PANI or pseudo-ANI to provide a level of near real-time location reporting from the Voice over IP provider's network. This was actually a reuse of technology that was developed to deliver Phase 2 cellular location information to the PSAPs. Today, the NENA Technical Standard Document, NENA 08003 version 1, provides a detailed functional and interface specification for the NENA i3 solution Stage 3. It defines an end-state vision and framework to deliver location and additional information via an intelligent IP network known as an ESInet or ESInet. Information is conveyed in the SIP invite header in a special location object known as PIDF-LO, which is a Presence Information Data Format location object. PIDF-LO contains geodetic location information, I'm here, come and get me, as well as additional data by way of specific URLs that can contain information such as floor plans, maps, smart building sensor information, or even personal medical information if a user chose to opt in. The most significant change with NENA i3 is that the ANI-ALI databases are no longer required or even relevant when the emergency caller is using a SIP-based NENA i3 compliant device, as that device will send the location information. Additionally, with the ANI-ALI databases no longer being required, the need for expensive mileage-based camera trunking is also eliminated. This promises to drive the cost of the network down and allow those monies to be redirected to a next-generation 911 infrastructure. So why move to next-generation 911? Well, some of the drivers are increased capabilities, reduce and control the costs, and increase capacity. Now, we don't increase capacity necessarily by adding trunks. We increase capacity by using network intelligence based on the information being conveyed to the PSAP to prioritize and route specific callers. Additional capabilities are added, such as GIS map and CAD integration, and geospatial call routing based on location data provided. We can also look at SMS, real-time text, and multimedia, including video and images. And that's all delivered through a SIP NENA i3 compliant environment. Moving to next generation 911 can help PSAPs consolidate to control costs, look at software as a service offerings or hosted NG9-1-1 PSAPs. Basically, allowing your call takers to exist anywhere that a broadband network connection exists. Leveraging your existing investment can be done through several different mechanisms that we'll show you shortly. One of the greatest reasons to move to Next-Gen 911 is capacity. Because we're using a managed IP network, or ESInet, we can more intelligently look at our call traffic, make decisions, and more effectively handle spikes in volume. For example, if you're a two-seat PSAP and you've got a major highway running through your town, you know that whenever there's an accident, you'll get 25 to 30 calls from motorists and their cellular phones. If your PSAP has implemented an overflow policy, your two call takers are immediately taken out of service with the first two calls. Overflowing to towns next to you proceeds to take those towns out of service as their call takers get inundated with the inbound call traffic. Adding more trunks doesn't solve the problem. That just puts more people in queue at your PSAP. And then, what about the poor guy calling in with a heart attack from across town? He's either going to be waiting in queue or transferred to a town that may not be able to dispatch. Using the intelligence in the network, we can look at things like caller location and establish caller proximity to existing emergent events. And while one call taker is working through those calls as quickly as possible, other callers with close proximity can be given network treatment, such as an IVR, saying that their call will be answered momentarily. However, it's been noted that they're in close proximity to a known incident. If they have additional information, they can stay on the line. If they were just being a good Samaritan, we have their telephone number. We will call them back once the traffic load clears. With your other dispatcher left free for calls not associated with that particular incident, they're there to take the call from across town based on a location decision. And that's just one example of how we can use additional information and workflow management based on caller data. One of Avaya's key values is we've been delivering telephony to some of the world's largest contact centers around the world. The day after Thanksgiving and the day after Christmas, when everyone is calling to return gifts, we take millions of calls. We understand how to build resilient networks and power some of the world's largest financial networks. Critical reliability is something that we do well, and we've adapted that technology for even higher standards for use within public safety. The Avaya Next Generation 911 solutions encompass three major pillars in the 911 network. We provide enterprise-class communication servers servicing small, medium, and large businesses that can provide intelligent user location information that can now be conveyed by the way of PIDF-LO on a SIP-enabled IP trunking network. In the network, we can provide the intelligent IP-based call routing functionality in elements such as the Emergency Services Routing Proxy, which replaces today's selective router. We also enable our DevConnect technology partners, such as Synergem, to build out and manage next-generation 911 ESI networks required to deliver next-gen 911 services. Finally, at the PSAP, again, with our partner Synergem, Avaya delivers the core infrastructure that's required for the next-generation call-taker desktop and network environment in either a CPE-based or hosted environment. Interagency routing is a critical requirement for legacy 911 networks today. However, the mechanism is one that requires the agency to often invoke a star code transfer on the selective router. The call is initially delivered to a primary PSAP, where the anti-alley bit is performed to obtain the caller location. Audio logging and recording is performed locally and stays with that agency. In many cases, though, that caller has to be transferred to another agency. When the caller is redirected to the secondary PSAP, the alley and ante information must again be obtained by that new center, and a separate recording session is started for audio logging of the call. If a third agency becomes involved, once again, a star code transfer is invoked on the selective router or 911 tandem. As in the previous cases, the third agency receives the call in the same fashion, and again, must bid for the anti-alley information of that caller, and then invoke its own recording and logging sessions. As you can see, there is no interagency connectivity. Service is provided over a very limited geography, and there is extremely inefficient and disparate logging and recording in place. Additionally, the network itself is built around a costly, mileage-based CAMA trunk infrastructure that is difficult to expand or redirect and is limited in its ability to convey multimedia information. In addition to leaving important details behind, each agency in the chain of care loses a complete view of the incident, in addition to making the post-incident forensics difficult to assemble as the information becomes fragmented across the public safety network and different agencies. To improve on interagency collaboration and enable the sharing of data, the NINA i3 architecture defines a bridging model in Section 5.7 of the 08003 Next Generation 911 Framework document. The caller and any contextual data received is centrally anchored on a media application server or conference bridge. Then workflow engines in the network can examine the data and then make an intelligent choice of which call taker is best suited for any particular call. Once a call taker is selected, they are then invited to the established conference bridge, where they immediately have access to the caller, as well as any additional data such as location, SMS, MMS, video, or any other additional data that's available. Additional resources such as session recording can also be added to the conference to satisfy any logging requirements. This architecture eliminates call transfers and the potential loss of data during a transfer, as additional resources can be joined to the original conference where they also have available to them any of the existing data that was previously collected. Avaya calls this model Persistent Contextual Collaborative Conferencing, or PC3. As ESInets are built and deployed over a wider geographic area, interconnectivity is provided in much the same way the public internet is designed. That is, a network of networks, using resilient, managed IP backbones over standards-based infrastructure that provide complete connectivity between any agency or entity attaching to that network. As the next-generation ESI networks are built, connectivity to legacy PSTN networks and legacy PSAPs will still be required for a short period of time. Since legacy 911 cannot be upgraded to support next-generation 911, the mechanism for supporting these environments is a gateway model. Legacy PSAP gateways, as well as legacy network gateways, are positioned at the edge of the ESInet and provide TDM to SIP and SIP to TDM conversion. Many other technologies talk about bridging the gap or transitioning to the new next-generation 911 network. But in reality, an analog camera trunk is capable of only two things: a voice path from the caller and multi-frequency tones that signal a database reference for location. That legacy network is not capable of anything else, therefore it cannot be a bridge of the technology or a transition. Remember, legacy E911 deals with Annie and Allie. True next-generation 911 deals with PIDF-LO and additional data provided via IP Ethernet. Just because a solution has an IP endpoint doesn't make it I3 compliant. In fact, the technology that connects the endpoint telephone is irrelevant. As long as there was integration with the desktop software, there's no reason why you couldn't use a 1956 Bakelite rotary telephone for your audio source. But I recommend you use some of the new stuff. Once an ESInet is put in place, next-generation PSAPs can connect directly in the ESInet, and their calls will be delivered over SIP. Anyone living outside the ESInet boundary, at a carrier level or a PSAP level, simply maintains connectivity to a legacy network gateway or a legacy PSAP gateway using the existing equipment they already have in their network. The gateways are typically provided by the existing ESInet provider. Avaya maintains a significant presence in public safety. Employees maintain active memberships with several industry forums, as well as NINA ENP certification. We are key contributors to several important work groups in the 911 space, and some of our contributions include the Joint Operations and Technical Wireline Wireless Quality Assurance Working Group, the NINA Multi-Line Telephone System Model Legislation, ESInet Network Design, Next Generation Additional Data, the Master Clock Standard, and the Next Gen 911 Transition Plan, just to name a few. Our public safety team maintains a landing page on the web at avaya.com/public safety, where you can find solution videos, brochures, case studies, as well as grant assistance programs to assist in funding your evolution to next generation 911. We're very active in social media and produce a weekly blog and podcast dedicated to public safety. You can read about these on the Avaya Connected blog at www.avaya.com/Fletcher. They're also available via podcast at fletch.tv or on YouTube at youtube.com/Fletch911TV. We appreciate you taking your time to view this webinar today. And if you have any questions that need to be answered, feel free to reach out to your Avaya representative or contact us directly.